Hello students, welcome to Sri Jayendra's Ring Zone classes. I am your friend and mentor for coming classes with respect to physics. This is lecture number 1 of a unit Thermodynamics. Let's begin with today's session. In this session we are going to discuss about the introduction of thermodynamics. So let's begin. We can say what thermodynamics is. It is a branch of a physics that deals with the concepts of heat, temperature, and the internal conversion of heat and other forms of the energy. It is basically the combination of two words. One of them is the thermo, and the other is the dynamics. Now, what thermo and dynamics means? Let's have a look. Thermo represents the heat, and dynamics represents the movement. So we can say thermodynamics is the branch of a physics which deals with the relation between thermal energy and the mechanical work done. It is responsible. Thermodynamics is responsible for the conversion of heat energy into work and vice versa. That means from work to heat energy. Heat energy, whatever we are providing to a system, will give rise to increase in the temperature of the system. And when when energy is given to a system, it hits up and takes energy from the system, then it will be a cool up. I hope this is clear. So let's take an example how this heat energy is being converted to a work. In a steam engine, the heat of the steam is used to do the useful work that we understand. When we say it is used to do the work, we mean it's a moving, they are moving the piston, which in turn rotates the wheels of the train, and so on. Light, electrical, mechanical, chemical, nuclear, sound, or thermal energy itself can cause a substance to heat up by increasing the speed of its molecules. And different types of energy can be converted to a heat energy. Let's take an example of conversion of energy into a thermal energy, I should say heat energy. So, mechanical energy is being converted into thermal energy whenever you bounce a ball. Each time the ball hits the ground, some of the mechanical energy of the motion of the ball is converted into the heat energy. So the ball slow down at each bounce due to the loss of this mechanical energy. One more case, when a vehicle is moving with constant speed, the brake has to be applied frequently. And when this brake is being applied, so the work is done against the friction and which is converted into heat, and hence this drum gets heated. I hope this is clear. One more case, let's take a look. An electrical energy. An electrical energy is being converted into the thermal energy when you use objects such as the heating pits or electrical stove elements or toasters or hair dryers. Even you can take the electric bulbs. In this situation, that electrical energy is being converted to heat energy. So there are several examples, there are several explanations of conversion of other form of the heat, other form of energy to the heat energy. Let's take the another example that light from the sun is being converted into heat, and as the sun rays warm the earth's surface, and we know that the sun transfers a thermal energy and light energy to plants for the preparation of the food by the process that we call as a photosynthesis. So this is a one form of conversion of one form of energy. Here it's a light energy to certain another energy. So this is how the energy conversion do take place. Energy due to friction creates a heat energy. Let's take an example, a process of rubbing hands, and that generates the heat. If you rub your hands for larger amount of time you will feel warmth of it. Yes, this is what, this is just the conversion of friction, or this is what we can say, it's a conversion of one form of energy to another form of energy. I hope this is clear. So this all are the conversion of different forms of energy to heat energy. I hope this is clear. Is it clear? Is it? Great. Now let's take certain quick questions. The motion of atoms or molecules that creates a form of the energy is known as the, yes, kinetic energy, no. Potential, no. Chemical energy, I said no. It's a thermal energy. Great. Next, a second, it's a friction can generate force, no. Mass, no. It generates heats, yes. This is clear. Next, let's look at the types of the different systems. Let's discuss the different types of system. First, let's define certain words first before defining the different types of systems. We have generally mainly three statements, three words every time we are going to deal with this. It's the first is the thermodynamic system, another is the surroundings, and then will be the boundary. So let's first define what system is. When we say a define, we can define that it is a region in space, and that region may contain a collection of large number of atoms or molecules within a real or imaginary boundaries. Now, what is surrounding? Surrounding is the medium or matter that surrounds the system, which may participates in the process of exchange of matter or energy with the system. This is the surroundings. And let's look at the case of the boundary, what it is. It is the real or imaginary surfaces. It is the real or imaginary surface that separates the system from its surroundings. That is what we call as a boundary. I hope this is clear. Is it clear? Is it? Are you sure? So, this is the situation that, let's suppose this is the system, then this is the boundary of the system. That means that I'm going to look into only this specific region. Whatever happens in this specific region, in this system, it is my area of observation. Other than this, I don't mind anything. But this is the surrounding, and this can have exchange of energy, or this can have an exchange of matter too with these systems. Yes, let's look at the thermodynamic state variables. It is, or they are the parameters which determine the state or condition of a system. These parameters will which will be determine the state or condition of a system, and they are called as the thermodynamic state variables, such as there are pressure, volume, temperature, internal energy, etc. So there are certain variables that we define as the thermodynamic state variables. Now this thermodynamic state variables could be divided into two categories. One are the intensive variables, and the other are the extensive variables. So we are going to discuss intensive and extensive, but before that we need to discuss something very important, that is the type of system. We have basically three different types of system. One is the open system, another is the closed system, and the third one is the isolated system. So let's look what one by one, what open system is, what closed system is, and what isolated system is. So when we say open system, it means the system which can exchange both matter and energy with the surrounding is known as the open system. So let's look at that. This is my system, and anything that is around this anything that is around this is known as the surrounding. So as you can see this, that this is open. That means even energy as well as matter can come into the system or can come out from the system. Let's take in case it's a cup of coffee. Yes, it can take energy from the surrounding, and or it can give its energy to the surrounding. When it is a hot coffee, that means it can give its energy to the surrounding, and this is the way how it cools down, that we have discussed even in the thermal properties of matter, in a way of Newton's law of cooling. Yes, it was the same approach. Even it is open for the matter as well. So this kind of systems are known as the open system. What is closed system? In that situation, it is the system which can exchange only energy, but it cannot exchange matter with the surrounding. Is This is what we call as the closed system. So this is the closed system, this is the system, and anything around it is known as the surrounding. So when we discuss the closed system, that nothing is going to be exchanged between this system, that nothing is going to enter into the system, neither anything is entering nor anything which is leaving the system. That is what we call as a closed system. Let's take an example. A tightly kept cup of coffee is the case of the closed system, or we can say it's a pressure cooker with a closed lid is the case of the closed system. So this is the situation, this is system, this is surrounding, and there is only the exchange of energy between system and surrounding. That means nothing is going to be added, nothing is going to be removed. I hope this is clear. Great. Next is the isolated system. It says that the system which cannot it is the system which cannot exchange energy and matter with its surrounding is known as the isolated system. So in an isolated system, no, this is the system, they are not going to exchange matter, they are not going to exchange the energy, that kind of system. So neither matter nor energy is going to be exchanged. This is what we call as the isolated systems. So let's take an examples of different isolated systems. It's a coffee in a closed and well insulated thermoflask. Yes, even you have seen this certain stainless steel flask are there in the market, that they can keep the object hotter or colder for several hours of a time. So that is what we call as an isolated system. That is, they are not going to receive anything, they are not going to delivering, neither delivering nor receiving energy from anything from system. I hope this is clear. Now let's we were discussing about the extensive and intensive variables. So what are the intensive variables? They are independent of amount of mass, that is what we call as an intensive variables, such as a temperature. It does not depend that how much is the gas, it just depends on the hotness or coldness of a body. Next is the pressure, next is the density. So this all are the variables that are not depending on the amount of mass. Whatever could be the amount of mass, their property remains the same. Next case, it is the cases of the extensive variables. And when I say they are the extensive variables, they are dependent and very directly with the mass. That is what we call as an extensive variables. So they are mass, volume, energies. So this all are the variables. This all are the variables which we know as the extensive variables. I hope this is clear. Is it clear? Is it clear? Great. Now let's look at certain quick questions. Blank are the thermodynamic state variables. Pressure? Yes. Volume? Yes. Temperature? Yes. Yes. All of the above. Yes. This all are the thermodynamic state variables. Second, intensive variables. Intensive variables are independent of amount of, yes, intensive variables are independent of amount of mass. Yes, great. Next, next, blank variables vary directly with the mass. Yes, they are the extensive variables. They are the extensive variables, just as the mass itself, energy. So this all are the variables which varies with the mass. Next, the system which can exchange both matter and energy with the surrounding. Yes, one who is going to exchange both, it is the open system. Next, pressure cooker with a closed lid. Pressure cooker with a closed lid is an example of closed system because it is going to it is going to exchange an energy but not the mass. It is going to exchange an energy but not the mass. That is what we call as a closed system. Next, in an isolated system, there is no exchange of blank with the surrounding. Yes, they are not going to exchange matter as well as they are not going to exchange an energy when we say it's an isolated system. So this all are the basics. This all are the basic terms that we are going to use, that in from the next time when we asked or when we just introduce that this is closed system, that means you will understood by itself that this flow of is possible, this flow is not possible. When we say this is the open system and situation and it's these are the state variables, that means you understand that yes, it's a open system. That means you can exchange energy with the surroundings, you can exchange matters as well. So these are the basic terminologies that we use to understand the thermodynamics. Now let's discuss the zeroth law of thermodynamics. Let's have a look. First, to understand the zeroth law of thermodynamics, we must understand a word and which is very important, which is thermal equilibrium. It is the any state of a system in which the thermodynamic coordinates remain unchanged is called a state of thermal equilibrium. And what we can say is that who will define the thermal equilibrium is that if two systems are said to be in thermal equilibrium with one another, if they are at the same temperature, this leads to the zeroth law of thermodynamics. But we learn a very important aspect of the equilibrium is that these two systems are said to be in thermal equilibrium if they are having the same temperature. If they are not having the same temperature, they cannot be considered as the thermal equilibrium. Let's suppose understood that we have three systems over here. It's a B, C, and let's call this as an A. Let's understand that pressure at B is P and its temperature is T. Its volume is V. Let's call the C, that let's suppose pressure at C it's a 2P, its temperature is V, and let's call this its volume is V by 2. So if what can we comment on their equilibrium status? So what we understand is that as this both are having same temperature, as this both are having same temperature, so as they are having same temperature, they are said to be in a thermal equilibrium. I hope this is clear. Is it clear? Is it? Do you have any doubts up till now? As they are having same temperature, they are said to be in a thermal equilibrium with each other. Now let's suppose the situation is they are having the pressure P. This is having temperature 2T. This is having volume V. And this is having pressure P. It's having temperature T. Let's suppose this is having a volume V. So you can see that pressures are equal, volume equal, temperature not equal. If temperature are not same, they are not in thermal equilibrium. I hope this is clear. So it is only the temperature who will decide that whether those systems are in thermal equilibrium with each other or not. So what I should write it down that it is the temperature that decides equilibrium. That means if two systems are at same temperature, then they are said to be in thermal equilibrium with each other. If these two systems are said to be in thermal equilibrium with each other, that means they are having same temperature. I hope this is clear. That means if two systems are at different temperature, they are not said to be in a thermal equilibrium with each other. Please notate this, as well as we must be very clear. We must be very clear with this aspect that temperature will answer me that yes, we are in equilibrium, no, we are not in equilibrium. He is the final authority to define an equilibrium. So let's now we can switch to the zeroth law of thermodynamics. So what does it say? Let's see. It states that if two systems are in thermal equilibrium with the third system separately, then the two systems are in thermal equilibrium with each other as well. That means let's look. We have three systems: a system A, system B, and system C. These are the three systems. And what I can say is, let's say that system B is in thermal equilibrium with system A. A system C is in thermal equilibrium with system A. That means this B is individually in an equilibrium with A. The system C is individually in an equilibrium with the system A. So if these two are separately, if these two are separately in equilibrium with each other, then B as well as C, these two must be in thermal equilibrium with each other. This is the situation. I hope this is clear. Is it clear? Great. So let's suppose that the temperature of the system A is equal to the temperature of the system C. That means TA is equals to TC. Now let's suppose that in addition the temperature of the system B is also equals to the temperature of the system C. That means TB is equals to TC. So that A and C are in thermal equilibrium with each other. This is what zeroth law of thermodynamics is. That if these two are at a thermal equilibrium, that let's suppose B and A is in thermal equilibrium with each other, C and A is in thermal equilibrium with each other, then B and C must be in thermal equilibrium with each other. This is the statement, and this is the conclusion from the zeroth law of thermodynamics. So zeroth law of thermodynamics leads to the concept of temperature. What we determine is that temperature determines the degree of relative hotness or coldness of a body, and it will give us the direction of flow of hot and flow of heat energy. And this thermometer, the thermometer works on the principle of zeroth law of thermodynamics, a temperature scale that we have studied and that we have discussed as well in the thermal properties of matter. This temperature scale was designed on the basis of zeroth law of thermodynamics, and mathematical form of zeroth law of thermodynamics is that function of pressure and volume will be the constant. This is the mathematical form of zeroth law of thermodynamics. I hope this is clear. Is it clear? Is it? Great. So let's look at certain quick questions. The question says that the two systems are said to be in thermal equilibrium with each other if they are at blank temperature. Yes, if they are at same temperature, they are said to be in a thermal equilibrium with each other. Next, if two systems are separately in thermal equilibrium with the third system, then the two systems are in thermal equilibrium with each other. And this law is known as the, yes, this is known as the zeroth law of thermodynamics. Next, blank is the blank is the thermodynamic variable whose value is equal for two systems. Blank is the thermodynamic variables whose value is equal for two systems which are in thermal equilibrium. Yes, so temperature is the thermodynamic variable whose value is equals for two systems which are in thermal equilibrium. He is the final authority. Yes, now let's discuss next very important aspects of the thermodynamics. It's a heat, work, and internal energy of the system. So let's begin with the heat first. When we say heat, it is the form of the energy that transfers due to temperature difference between the system and the surrounding. And heat is always flowing from the body at a higher temperature to to a body at a lower temperature by itself. That is the, let's suppose, understood that this is the system and this is at temperature A, and this is another system, this is at temperature B. Let's assume that TA is greater than TB. If this is the situation, that if TA is greater than TB, then heat should flow from this to this. Heat should flow from body at temperature A to the body at temperature B. This will be the situation. I hope this is clear. This is the situation where TA is greater than TB. I hope this is clear. Is it clear? Is it? Are you sure? So the net flow of heat stops when the temperature gets equalized and the two bodies are then said to be in a thermal equilibrium. That means, let's suppose this is at, let's call it 80 degrees Celsius. This is at 50 degrees Celsius. So heat will start flowing. Heat will start flowing from 80 degrees Celsius body to the body at 50 degrees Celsius. And this flow of energies will continue until both have reached on the same temperature. When and when these two are at the same temperature, when they are at the same temperature, that means the flow of energy will stop, and they are said to be in a thermal equilibrium. But let's suppose the situation is that we have two systems, that is, let's suppose this is A, this is B, and let's call them that both are at 40 degrees Celsius. Then there should be no flow of it from either way. No, this is not possible because it is the temperature difference which, due to which heat flows. If there is no temperature difference between these two bodies, then there is no flow of heat would take place. I hope this is clear. So if temperature difference is there, heat will flow. If no temperature difference is there, if no temperature difference is there, that means no heat flow would take place. I hope this is clear. Is it is it clear? Great. Now let's discuss the work. It is the energy that is transferred. It is the energy that is transferred from one system to another by the application of force at a point moving in its own direction. That is what we call as a work. So it is the energy that is transferred from one to another system, and that is what we call as a work. Work is done by the system when when heat energy is added to the system. So work is done by the system when heat energy is added to the system, and dW is positive when work is done by the system, and dW, it's a work done, is negative when work is done on the system. Even we are going to discuss this when we studied the first law of thermodynamics. But this is the basic mechanism of work, that when and when we have the situation such that we have applied a force, and due to that force a displacement of a system is achieved, then we can say a work is done. When it would be a positive, when it would be a negative, that we will discuss later on, but up till now this should be the clear. Next, heat and work in thermodynamics are not the state variables. They are not the state variables. They are the path variables. And when I say they are the path variables, that means they depend on the initial position, they depend on the final position, as well as they depend on the path taken. So they are the modes of energy transfer to a system, resulting in change in its internal energy, and this internal energy is said to be a state variables. So this is the situation, that only the state variable depends on this two only, but these variables are the initial system, final, as well as path taken. So these are the path variables and these are the state variables. Let's discuss internal energy. We can say that internal energy of a thermodynamic system is the sum of the internal kinetic energy due to a molecular motion, and internal potential energy due to molecular configuration of all the particles in the system. So basically it is the addition of total kinetic energy of the system plus total potential energy of the system. That is what we define. That is what we define as the internal energy of the systems. I hope this is clear. So what we were discussing was path variables and not path variables, that all those variables that are dependent on initial position and final positions only, final positions only are are known as the state variables. Yes, so this all are the variables that are dependent on initial position and final position. Yes, they depend on the initial position and final position. They are known as the state variables. Like, it's an example is the internal energy. It's an internal energy that depends on the initial position and final position only. Now, there are other variables too. All those variables. Let me rewrite this. So it is the all those variables that depends on the initial position, final position, as well as path taken, to reach initial to final position is known as the path variables, such as we can say delta Q. It's a heat energy. Or delta W. It's a work done. So this depends on everything. This three things. They depends on the initial position. They depends on the final position, as well as they depend that from you have reached from initial to final, which path you have taken to travel from initial to final. Even that is what they are dependent on. So these are known as the path variables. Please keep this in mind. Now let's discuss of Joule's law for to understand in a better way a heat. It is the amount of mechanical work performed is directly proportional to the amount of heat produced. That is what we call as work done is directly proportional to the heat energy. And if I remove this proportionality constant, then it would be a work done is equals to J into H, where this J is known as the it is the mechanical equivalent. It is the mechanical equivalent of work required of heat, or that is what we call as a Joule's constant. SI unit of Joule's constant. This is J, which is equals to W by H. This SI unit of J is the Joule per calorie, and its value would be equals to 4.186 Joule per calorie, or it's a 4.186 into 10 to the power 7 or per calorie. I hope this is clear. Is it clear? So and work when heat and work are in SI system, then we can say it's a J is equals to 1. I hope this is clear. Now let's discuss the various applications directly, as we have used it in many of our examples as well, in the work power energy, or maybe in the laws of motion, or maybe in the thermal properties of matter. We are just revising it so that if any of the questions can be asked from it, we can directly have a deal with it. Let's discuss the applications of Joule's law. Let's suppose the situation is that, let's suppose it is the ice cube, and let's suppose it has been dropped from here, and it travels with the height h, and let's suppose this ice is being melted over here. So what we understood is that work done is equals to Joule into H, and this work done that needs to be done, it's an M into G into H. It's a change in potential energy, or I should say loss in potential energy. It's a mgh. That would be equals to J into ml. Why? Because this is going to melt, and when there is something which is melting, it's a Q is equals to M into L. So this is Q equals to M into L. So from this it's an H, because this has gone. It's a J into L by G, where L could be given. L could be the latent heat of ice, with it is 80 calorie per gram. Yes, I hope you remember this. Or let's suppose if it is the case that when it falls from a height h to the ground, it will just have the change in temperature. So what will be the situation? The situation would be work done or loss in potential energy, that is the mgh, and that is going to be converted to the ms delta theta. Yes, so for ice, s will be equals to half units, or from delta theta it's a J into L divided by M into G, where S is the specific heat of the water. I hope this is clear. Let's take one more example. Let's suppose when a body of mass M is moving with a velocity v, is stopped, and all of its energy is retained by it, then the increase in the temperature. This is the situation that it is having the kinetic energy, and let's suppose it has stuck to it, and its velocity came to an end. That means all of its energy has been used has been given to this block. So the increase in temperature of this block could be written as its energy, that is what we have is the half mv square, and that is being converted in a form of it's a J into ms delta theta. So from this, it's a delta theta which is equals to v square by 2js. I hope this is clear. Is it clear? Correct. So if a bullet, let's suppose one more case, if a bullet just melts when stopped by an obstacle, and if all the heat produced is absorbed by the bullet, then basically it is going to perform two tasks. That first, it is going to change the temperature, and then it is going to melt it. So when it is in a phase to state, in a phase to change the temperature, that means, let's say ice cube is there and which is at minus 20 degrees Celsius, and I need to melt this. Then what I need to do is, first transition, it's from minus 20 to 0 degrees Celsius, and the second transition would be from 0 degree to 0 degree. Yes, so minus 20 to 0 and then 0 to 0. Minus 20 to 0 will be performed by this. It's an ms delta theta. And 0 to 0, that is done by this ml. So this ms delta theta plus ml would be given as half mv square divided by j. Where? Where L is the latent heat of the material of the bullet, and S, it is the specific heat of material of bullet. I hope this is clear. Is it? Is it clear? Are you sure? Do you have any doubts up till now? Do you? Do you have any doubts? Is there anything? Is there? No? So, what we can say is that heat and work are two distinct modes of energy transfer to a system that results in change in its, yes, that it results in the change of the internal energy of the system. Let's take a second one. So internal energy is the sum of the molecular blank in the frame of reference relative to which the center of mass of the system is at rest. Yes, it is the sum of the molecular kinetic energy plus molecular potential energy. That is what make internal energy of the system. Next, when when heat is added when heat is added to a system at constant temperature, when a heat is added to a system at constant temperature, which of the following is possible? So when heat is added, internal energy of the system increases. We cannot claim it. Work is done by the system. Let's think. Neither internal energy increases nor work is done. No, this is absolutely incorrect. Internal energy increases and also work is done by the system. No. Yes, it's a work is done by the system. There are certain systems that can create that delta Q directly to the delta W. We are going to discuss the that processes in the next sessions. I hope this is clear. So let's wind up this session over here. This was all about the introductory session of the thermodynamics. We have learned very basics terminologies that we are going to use in the next sessions of the thermodynamics. So please be very careful while go through this session, that this is not probably having any numericals, but this is very important, because from the next session, from the next classes, from the next lectures, we are going to discuss directly that variables. We are going to use directly that terminology, and you must understand the theme, the feel behind that terminologies. I hope you understand this thing. So please go through this, and before you tune on to that video, please be much comfortable with this all terminologies. Thank you. Have a good day. Take care. Bye.